students. So, in the last class, I did a small presentation on gravitation and most importantly, the universal law of gravitation. Now, today I'm going to move forward with today's topic on the acceleration due to gravity and the free fall. Right? Okay. Free fall here. So what actually you think about free fall means something which is falling up from the sky, right? For example, okay. Okay, there is a building. On that building, there is a person here. Now, if that person is going to jump, we are very sure that he is going to die from that particular position there. Why? Because that particular person, when he jumps, for example, if he applies some more force to jump from that side, his speed is going to increase as he moves down to the building, right? So the point is, what I'm trying to say is that if a person, let's say, if a person jumps in that direction, he will also move down here. Now, why do you think this is happening there? Why? Because there is a presence of gravity there. So any kind of object which falls under the action of gravity is what we used to call as free fall in a simple sense. For example, if I'm going to throw this chalk up there, this chalk will move to a certain point. From this certain point, this chalk is going to move down. This will move down under the action of gravity. So such kind of fall is what we used to refer as free fall. Understand? So let's say this particular person is experiencing a free fall right now over here, right? Okay. Falling under the action of gravity. Falling under the action of gravity is what we used to call as free fall. Now, in the last class, we talked about the universal law of gravitation. Now, according to that law, what they had discussed is that, for example, here, this is Earth, and between Earth and an apple here, I have given an example of an apple and an Earth here. Between these two, there is an attractive force which is moving downward there. This particular force is what we used to call as gravitational force, right? Okay, so this gravitational force is going to be given by Gm. I'm going to write this capital M and small m divided by, let's say, r squared. In the previous video, I have referred this r as d squared. Now it doesn't make any difference here. Okay? Now, according to Newton's second law of motion, okay, what we have talked about is that force is, or can be also written as mass into acceleration. Right? Okay. Now this force can be also written as mass into acceleration, which I can also write as G capital M small m and divided by r squared here. Now this small and this small m, they somehow cancels, and we got this particular A, G capital M and r squared here. Now what is the importance of this particular formula over here? Look up here, this particular formula over here. What is the importance of this particular formula is that, as we have discussed before in free fall, we have somehow understood that all the objects which are present, all the matter which are present on the earth, they are experiencing some sort of like gravity because of the earth's surface. Now we are trying to understand what could be that gravity, how much amount or how much scale the earth is experiencing the gravity towards the particular kind of object. Okay? So let's say here, now we got this acceleration is equal to G M capital M divided by r squared here. Now what is important for you to know is that we know the value of G, but we should be able to understand what is that capital M and what is that r squared here. Understand? So now let's imagine, I'm going to take this example once again here. This is Earth and this is apple here. Understand? And this apple is having small m and this is capital M, and between that there is a presence of some amount of distance here. Okay? Now, If I relate this one with that, what I will be able to see is that this particular apple is falling down towards the earth. We have never seen something like this bird moving towards the apple. But instead we have seen, this is common sense, the apple falling down. Right? Okay, so now this particular capital M is this particular M, and this small m is the mass of the apple here. Okay? Now in order to get this R is the radius of the earth. Radius of the earth. Now in order to get a particular kind of value for acceleration, we are cancelling this two and we got this value here. Okay? So now I'm going to write here A is equal to capital G, capital M divided by R squared here. Now how much is capital G? Can you look up here? Capital G is 6.67 into 10 raised to 4 minus 11 here. What about the value of mass? 6 into 10 raised to 4, 24 divided by. What is the value of R here? Value of R is 6.37 into 10 raised to 4, 6. That is whole square here. Okay. Now, it is not important for you to cancel out all of this. But in case if you can do it, you're going to get the value that is 9.8. Understand? And this we are always going to write in meter per second square. Now this is the value of A. Now this particular A is normally we used to talk in terms of motion in a particular kind of straight line, or acceleration is what we used to refer. But in this case right now, this is 9.8 meter per second square. This kind of acceleration is being faced by that particular apple towards the earth, which we used to also write as G here, that is a small g. Understand? And this small g, the value of this small g, is what we used to call as acceleration due to gravity here. Okay? So, here. Okay, fine. So now I got the value G is equal to 9.8 meter per second square. Previously I used to take A, but in this case, this object is not moving in that direction here, a straight kind of line, but instead it is moving down under the action of gravity, which is why I'm writing this as G. Now, what is important for us to know is that why we are considering this G as an important, why we are learning this value of G is equal to 9.8 meter per second square. Right? Why? This G is also referred to as acceleration due to gravity here. Okay. Now the value of G is 9.8 meter per second square. Why this is important for us to know that? Right? Okay. So why this is important is that, for example, here, Earth, let's say Moon, then there is Jupiter here. Okay? I'm going to write this down. Moon, Jupiter. Okay? Now, Earth, Moon, and Jupiter, all these three planetary systems there, they have their own value of G. For example, in the case of Earth, we are having 9.8 meter per second square. In the case of Moon, it could be somewhere like 1.6 meter per second square. And in Jupiter, it's like 34 point something meter per second square. Okay. Now, as we see, 9.8, 1.6, 34 point something, right? Let's say 34.4, 6 or 5%, I don't remember. Okay, 34.5, let's say. 9.8, 1.6, 34.5. Now the value of G differs in Earth, Moon, and Jupiter. They are not same. So why this is important? Let's suppose imagine, okay. For example, there is a person here. There is a person here. Okay? So we were discussing about the acceleration due to gravity. Now let's suppose imagine, as I have put in an example right now, in the case of Earth, Moon, and Jupiter, with different kind of acceleration due to gravity there. Now, why we are learning that? Why this is important for us to know is because through the concept of acceleration due to gravity, we will be able to clarify mass and weight here. Now, normally, how we define mass is that mass is, for example, an object. This object is made of certain kind of matter. So, how we define mass? In the absence of gravity, for example, if there is a zero gravity in this classroom right now, and if I'm going to throw this chalk down there, let's suppose imagine this chalk is not going to move down, but instead it is going to float. But somehow, even if this particular chalk is floating up in the sky, what we will know is that this particular chalk is composed of some sort of matter, and these matters are constituted having some sort of mass there, which is what we used to define as mass here. So, how I define mass? The matters in object. Okay? Now, let's suppose imagine if there is an acceleration due to gravity here. For example, now this particular chalk right now, in this classroom, that is the reality situation here, we are experiencing some sort of gravity there. Now, if this particular chalk, let's say, in the absence of gravity, if this particular chalk is having a value of, let's say, chalk is having a value of 1 kilogram here, 1 kilogram. Suppose that, just an example here, 1 kilogram. Now, in the presence of gravity, the value is going to increase. Why? Because gravity is going to apply some amount of force on that. For example, that is what we used to define as weight. Normally, weight is denoted by W, and each weight, when we define weight, we always have to multiply mass into gravity here. Mass into gravity. Now, how much is the mass? 1. And in the case of gravity, that is in the case of Earth, is 9.8. That means how much we know that? 9.8. Understand? So, that is the point number 1. This is the point number 1 here. And whenever we are talking about the mass, we always have to write the unit kilogram here. Understand? We always have to write the unit kilogram. But when we talk about the weight, we always have to write the weight, the unit of weight in the form of Newton. Understand? So, normally, when we write weight, Newton here. Understand? So, this is 9.8 Newton here. Understand? Now, in understanding that particular importance of that 9.8, so now we will come to know that. Understand? For example, here. Now, okay, now let us imagine here. This particular chalk is 1 kg. In Earth, it is 9.8 Newton. Now, what about in Moon? In Moon, let's say, weight of this particular chalk is mass into gravity again. How much is the mass? 1. And how much the gravity? 1.6, which is equal to 1.6 Newton. That is very light here. And in Jupiter, it's like same 24.5 Newton there. Understand? Is that clear? So this is how we talk about weight and mass here, and both of them are quite different. And I think many of us, every one of us, we are getting confused with the mass and the weight. Now, whenever we talk about mass and weight, there is a presence of the important factor, that is the gravity, which plays a very important role in determining the weight or the mass of an object. Is that clear? Okay. Now, let us take my example here. Okay. There is a fat guy, and his weight, let's say, presently in Earth, in our measuring scale, if we measure like 100 kilogram here, right? What happens if that particular person goes to Moon? Now we have to know, right? So normally this particular person in Earth is 100 pound gravity. How much is the mass? It should be 10. And this gravity is 9.8. Instead of 9.8, I'm going to write 10 because in order to make this more simple for me. Understand? 9.8. Because if you write 9.8, it will be more confusing for you. So I'm going to round this one. I'll get the 10 here. So 10 times are 100, and this should be actually next here. But we are writing for our own comfort's sake, we are using kilogram here. Understand? Now this is the mass here. Now if that person goes to moon, we will find again m into g. How much is mass? 10 into 1.6. How much is that? This should be equal to, let's say 16. This should be equal to 16 Newton here. The very fat person, the moment he goes to moon, he becomes like 16. Now what will happen if he goes to Jupiter? Should be equal to W is equal to m into g. You think for yourself, right? So this is an assignment for you. Try to think about your own weight in Earth and think about the moon and the Jupiter. So I will continue the rest of the lesson in the next class with the Galileo's experiment. Thank you very much, all of you.